Hello everyone, myself Balasubramanyam, working as assistant professor in Department of EC, St. Martin's Engineering College. So today my session is about, I'm going to explain about the working of a junction FET. So before entering into our topic, I just want to give some clarification. That is, I will give some introduction. Okay. So my session consists of the following terms like it can I will give the first of all I will give the some introduction portion to the transistors. After that I will explain about the classification of field effective transistors. After that I will explain about the construction and working of the junction FET. So mostly my lecture covers about the junction FET working and construction. So after that I will list the few applications of the junction FET. Okay, so first of all, transistor. What is mean by transistor? So transistor is a three-terminal electronic device, so which is manufactured by the semiconductor material. Okay, so mostly these transistors are used in the switching applications as well as amplifier, that is amplification applications. Okay, so mostly we are having the two types of the transistors, where first one is the bipolar junction transistor and second one is the field effective transistor. So today I am explaining about JFET, which is a type of field effect transistor which we call simply FET or FET. So FET. So the definition for the FET is, in the name itself it is telling that field effect transistor. So in this transistor, the operation, that is the output current of the transistor is controlled by the voltage, that is input voltage we applied. So that input voltage will generate a field, that field affect the current of the device. So hence it is named as field effect transistor. So entering into the JFET concept, I just want to clarify, I want to distinguish between the BJTs and field effect transistors. Okay, so first one, FET is a unipolar device. FET is a unipolar device, which means that the operation of these device based on the only majority charge carriers, either it may be N or P, that is either it may be electrons or holes. Whereas BJT operation mostly depends on the both the charge carriers. That's why it is named as bipolar. Bipolar means the operation of BJT depends on the electron movement and also holes movement. Okay, so coming to the next one, it is a voltage controlled device. It is a voltage controlled device. The FET is a voltage controlled device because here the conduction is controlled by the applied input applied field. Okay, so due to that field, we are able to controlling the current, output current. Okay, hence it is named as the voltage controlled device. So coming to the BJT, it is a current controlled device. So we know the formula, that is output current. For example, if you consider a common emitter configuration, it is IC is equal to beta into IB, where IB is the input current. So output current is depends on the input current. So when we are changing the input current, that obviously change the device output. So hence it is a current controlled device. So next one is, it is having, that is FETs are having the high input impedance and BJTs are having the low input impedance. So most important thing is, whenever we are using an amplifier circuit, we are going to design an amplifier circuit, it should have the high input impedance, so which will give the high gain. So hence the FETs are mostly used for the amplification and switching purpose also. So next one is better thermal stability, and it is having the less thermal stability. So thermal stability means, so FET is withstand with the high temperature. It can operate effectively at high temperature values also. But when it comes to the BJT, it undergoes the due to the less thermal stability, thermal runaway concept will be occurred. It will provide there is some deviation in the operation. Okay, so next one, it is having the high switching speeds, whereas for BJT it is having the lower switching speed. So hence we are able to use the FETs in a switching applications in the digital circuits. So next one is, we can easily fabricate as compared to the BJT. FETs are easily fabricated, but BJTs are difficult to fabricate, because the construction is very simple. FETs are easily constructible because of their construction, but BJT is complicated as their construction is little bit different and complicated. Okay, so next one is, and one thing I want to rectify is, here FETs are of very less size and BJTs are with high size. So when size is less, we are able to use these field effective transistor in manufacturing of the integrated circuits, which are mostly used in our today's generation. Okay, so coming to the classification. So basically, I already explained in the first slide, transistors are two types. First one is the BJT and second one is the field effective transistor. So FETs are further classified into the JFET, that is junction FET. Second one is the MOSFET. MOSFET is nothing but metal oxide semiconductor field effect transistor. So coming to the JFETs are further classified into the N channel and P channel. So that is, it clearly mentioning that this N channel JFET operation, it depends on the electron movements. Hence it is a unipolar device. Similarly, it is a P channel device also same. Its operation depends on the holes only. So coming to the MOSFET. MOSFETs are a little bit different from construction features. So these are classified into the D MOSFET and E MOSFET. So here D MOSFET is nothing but depletion type of MOSFET, whereas E MOSFET is nothing but enhancement type of MOSFET. So further, for example, if a D MOSFET operation only based on the electrons, it is a N channel. Similarly, if it depends on the holes, it can be a P channel type of MOSFET. So totally we are having the 2 plus 2 plus 2, that is 6 type of field effective transistors we are having. But my lecture covers mostly about the JFET, which is of N channel. So N channel JFET I am considering, but the operation of P channel also almost all same, but the difference is here I consider the electron movement, whereas it considers the holes movement. Okay. So JFET. So JFET, as I mentioned, it is of two types. So those two types are, first one is N channel JFET and second one is the P channel JFET. So let us consider the construction, how it is going to look inside of the transistor. So here basically this JFET consists of, it is a N channel JFET. I am considering the N channel JFET. So here this is the whatever the block which is shown in blue color, it is a N type of substrate. Okay, that on either side of N substrate we are diffused by a material, P type material. Okay, which forms a PN junction type of structure. Okay, so PN junction, it forms two PN junctions, hence it is named as junction field effect transistor. So it is having the three terminals. So three terminals, those are named as source, that is source terminal, which is indicated by the S, and next one is the drain terminal, which is indicated by the capital D, and third terminal is the gate terminal, which is indicated by the gate. So if we observe, what are the functionalities of these three regions or these three terminals? Okay, so coming to the first one, source. So source is the place from where the majority carriers will enter into the device. For example, when we are going to work with this device, we are going to bias this device. In that scenario, this will enter, that is when we connect the voltage source, due to that majority charges will enter into this from this region, that is a source. Similarly, the drain is a point from where the majority carriers will leave the device. Okay, so after that, gate is the one more terminal which we are going to control the flow from source to drain. So indirectly we are going to control the current of this device by controlling the gate terminal voltage. So these are the three terminals, but there is one more thing, so which is the space between source and drain. So this is called as the channel. So channel is the path from source to drain where the majority carriers will transfer from this region to that part. Okay, so these are the three regions of JFET, and this is the construction of the JFET. Okay, so coming to this, as I mentioned, we are having the two types of JFETs. So first one is the N channel JFET, and its construction is, so if you consider here, it is a N type of substrate, whereas here we consider the P type of substrate. So difference is based on the arrangement, the same material we are using, but construction is little bit different. Okay, so these are the constructions of P channel JFET and N channel JFET. So these are the circuit symbols of N channel and P channel. If you observe here, the arrow indicates the current direction, and which, that is, the arrow into the device means it is a N channel FET, whereas arrow into outside the device, it is a P channel JFET. So whenever we are drawing a circuit, in that circuit, if you want to mention the JFET, simply we need to use these circuit symbols. Okay. So next one, working. So working means, so I want to give some clarity on that. So here junction FET, field effect transistor, here the operation can be done by one way, that is, here we need to control the voltage from that is current flow from source to drain to source by controlling the gate sources, I mean gate to source voltage. That is how it is going to done. So for example, I will explain this operation with the one example, that is I am considering the tap operation. So if you consider a tap, in the tap position, it acts as a source. I am assuming it as a source terminal, and I am comparing this with the JFET. Okay, so it is act as a drain terminal. Similarly, this terminal act as a gate. So initially, if you increase the current, it will reaches to a maximum value. That is, after that, if you further increase the charge carriers, but it maintains that value only. If you are able to change the gate voltage, that will increase the current or decrease the current based on the gate voltage. So this operation, that is JFET operation, we can simply compare with the tap operation. So here three terminals, as I mentioned. So here source is nothing but source of charge, whereas drain, where the destination that charge carriers will move. So that charge carriers movement can be controlled by this gate, that is this knob. Okay, so this knob acts as a gate here. So this is simple operation which we need to implement in terms of the device. Our device is junction FET. So if you observe this structure, so here we are having this is a channel, we are having source to drain, we are moving this charge particles by applying the voltage source. Okay, so whenever we are applying the gate voltage, this causes the change in depletion region or this width. So due to that, we are able to control the current. So hence it is named as it is a voltage controlled device. So hence I will elaborate this operation with the next thing. So next slide is working of JFET. So in this, so for example, as I mentioned, here, this is the actual biasing figure where I applied voltage source between the drain and source. Voltage source between the drain and source. Okay, so after that, here we are having the gate terminals, and these gate and source terminal are grounded. Okay, initially when we are applying the voltage, that is VDD, that is in between the VDS, when we are applying the VDS voltage, that will cause the electrons to enter into the channel. Okay, so for example, here when I am increasing the voltage, what happens is this depletion region width will increase. So that will cause the change in number of electrons. So that will cause the change in electron movement. But up to a particular value, the current will be increased. But after a particular value, these two regions will touch each other. But but it is practically it will produce the constant output. So whenever we are not applying any voltage at the gate terminal, but when we are applying the voltage at the in between the drain and source, and we are increasing the voltage, then it causes the increase in the current. After a particular point, it will reach us a saturation point. After that, it will give the constant output. Okay, so this is the actual operation of the JFET. So the point where it gives the constant output current is called as the pinch off point. That voltage where it starts the constant, it acts as a constant current source, it is called as the pinch off voltage. Okay, pinch off voltage. So if we observe this, so in this case, as I mentioned, here we are having the p type and n type, that is, it is a PN junction formed. Whenever we are applying voltage in between drain and source, due to that, when we are increasing the voltage, that is a positive voltage to the negative, here this substrate is the n type of material, hence we are applying the positive voltage. That is, for negative we are applying the positive voltage, that means it is a reverse bias condition, and that causes the increase in depletion region width. Okay, so that causes the change in output current. Okay, so this is all about the case 1 operation. So in this case, what I did is I maintained the VGS value, that is input voltage, is 0, whereas I applied the voltage between the drain and source, and which is VDS voltage. So initially I consider the 0 volts, from that I increase the voltage to a particular value, and it will give the curve like this. It will give the curve. So I have drawn the graph between the VDS versus ID. So, and when I am increasing the VDS value, it will increase the current proportional to the voltage, applied voltage. But after a pinch off voltage, that is, this voltage is pinch off voltage, after that it maintains the constant output. Okay, so this is the first case. I consider the first case. In first case, I am applying VGS as 0, whereas VDS is a positive voltage, or which is greater than the 0 volts voltage. So coming to the second one. So as a part, so this is the actual conclusion for the first case. So when we are increasing the VDS voltage and it reaches to up to the VP value, that is pinch off voltage, it maintains the constant proportionality between the voltage and output current. And after the pinch off voltage, it will give the constant value, that is constant current value. So this region is called as the saturation or pinch off region, whereas this region is called as the ohmic region, as it following the Ohm's law, that is V proportional to I. So here when we are increasing the voltage, proportionally current also increasing. Okay, so coming to the next case. So before entering into the next case, I just want to give some clarity on that pinch off point. Okay, pinch off point, because if you observe here, the depletion region width nearer to the source is very less, but at the top side, that is at the drain side, it is more. Why? So I am going to clarify this with one example. I am considering one example. Suppose I am considering this image. So this image, and so this image here. Okay, so now I just give you some clarity that here if you observe, when we are applying the VDS voltage in between source and drain, when we are applying VDS voltage, suppose when that is positive voltage I am applying to the drain terminal, and negative voltage to the this terminal. So whenever I am going to increase the voltage, So after a particular voltage, what happening means it maintaining the constant voltage. So suppose the channel, that is, if we observe, sorry, I will consider the, so let me explain with that a small diagram. So this is actual construction where it is having the n-type substrate, and here we are having the two regions. So this one is P and this one is P. So I will distribute it. So here the channel, that is from source to drain, the resistance is, that is the channel resistance is uniformly distributed. So I will consider it as the 4 resistances. Okay, let us assume it is R, 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 that is equal resistance values. So for this circuit, so I am applying VDS as 2 volts. I am applying VDS as 2 volts. So if you consider the resistance value, R equivalent is equal to R plus R plus R plus R, 4 R values, that is 4 R values, and the applying voltage is 2 volts only. So total 2 volts is divided into the 4 parts, that is each R is same value, right? So we can conclude that voltage drop across R is indicated that 2 by 4, so which is given by 0.5 volts, 0.5 volts. So we can say that here the voltage is 2 volts, hence at this point, due to the 0.5 voltage drop, the voltage at this point is 1.5 volts. Similarly, one more 0.5 voltage drop across this resistor, this will give the 1 volt as the output at this point. So after that, one more 0.5 decay in the voltage, that is voltage drop. Once again it will give the 0.5 volts here. After that, once again 0.5 volts voltage drop across this resistor, that will give the 0 volts as the voltage distribution here. So here the reverse bias voltage is 1.5, whereas here reverse bias voltage is 0 volts. So here more voltage when we are applying it for a reverse bias, that is, if we consider a PN junction diode, so the width of the depletion region will be based on the applied reverse bias voltage. When we apply the more voltage, more reverse bias voltage, this will increase the width of the depletion region. Whereas if we decrease the reverse bias voltage, then that will decrease the depletion region. Hence here reverse bias voltage nearer to the drain is more as compared to the reverse bias voltage at the source. Hence the width of the depletion region is more at junction nearer to the drain, whereas depletion region width is very less at the nearer to the source terminal. So this is the small clarity. So after a particular time, it will reach us to a maximum value. So due to the maximum value, these two depletion region will touch each other. So due to that, there is a case of ID equal to 0. But practically it is not possible, because when it is I equal to 0, that means voltage equal to 0. When voltage equal to 0, that will deviate the reverse bias condition. Hence it can large number of current will be flows through the device. Hence we are saying that after Vp, that is pinch off voltage, the ID value will be IDSS, which is nothing but saturation current. So coming to the second case. So second case nothing but, here previously we used the only gate terminal as 0. Now we are going to increase the gate terminal, that is we are applying the negative voltage. As always, gate terminal should be reverse biased in the JFET. Okay. So for that, I am considering the second case. Second case is VGS is less than 0 volts, that is negative voltage, whereas VDS is positive voltage. In this case, what happens means, here we are applying the reverse bias condition, that will increase the depletion region width, and that depletion region will penetrates into the channel, that will reduce the channel width, hence the current through that channel also reduced. That is, but at a particular time it will reaches to a maximum value which is less than the previous case. So if we observe that, so this is the drain characteristics of a JFET. So where first case is indicated by this line. So where we consider VGS equal to 0 volts. So after that, when we consider that is VGS volt, we applied the negative resistance value, that is minus 1 volt. So due to that, the channel width is reduced, hence number of electrons also reduced. Now it will be reduced to the current. So whenever we are increasing the negative resistance negative voltage value, that will increase decreasing the channel length, channel width, that will cause the decreasing in the current. So if you observe this, the points matching, the points here, this region is called as the ohmic region, where it obeys the Ohm's law. So this is all about the drain characteristics of the JFET. But after a particular value of VGS, that is when VGS is equal to pinch off voltage, that will make the device to off condition. That is, two depletion regions will touch each other, that causes no flow current, no flow of current in the device, that causes the device in the operate in the transfer off condition. So there is one more case where we need to consider the relation between the ID and VGS, that is input voltage and current value. So if you observe, this can be obtained by the drain characteristics, that is, so if you observe, when we are applying VGS equal to 0, we are going to get the maximum current which I am indicating here. So after that, when we increase the VGS voltage, that is when we apply the minus 1 volts, it will give the voltage which is here. So if you draw a graph in between the ID and VGS, it will give the exponentially decaying graph. So this graph is nothing but transfer characteristics of the JFET. Okay, so this can be indicated by ID is equal to IDSS into 1 minus VGS by VP whole square. So this is nothing but an exponential signal with a decaying function. Okay, so which is nothing but a Schottky equation. Okay, so this is the overall construction and working of the JFET with the VI characteristics. So total VI characteristics are classified into the two parts. First part is the drain characteristics, whereas second part is the transfer characteristics, which tells the relation between the drain current and VGS voltage. So similarly, if you want to observe the characteristics of the P channel JFET, so that I will explain by using the next value. One second. So this is the construction. If you consider here P type of substrate, so this is the P channel JFET. So this is the drain characteristics of the P channel JFET. So if you observe here, we are applying, instead of negative values, we are applied the positive values. Okay, so next one, applications of the JFET. Applications of the JFET are, so these are used in the low noise applications. So low noise amplifiers. So mostly due to the high input impedance, we are able to use this amplifier in the amplifier circuit design. Okay, so after that, differential amplifiers. So differential amplifiers are the building blocks of the operational amplifiers. Okay, in construction of the differential amplifiers also we use this junction FET as one of the part. So after that, constant current source. So when we are able to operate the junction FET in pinch off region or saturation region, it can be act as a constant current source. Similarly, it can be act as a analog switch. So last but not least, it is the most important application of the JFET, that is voltage controlled resistor. So JFET can be act as a voltage controlled resistor or voltage variable resistor. That is, when we are changing the VGS value, that is reducing the current value, that is increasing the resistance value. So that gives some relation between the resistance of the device and also applied voltage, that is applied voltage affecting the resistance of the device. So hence we can call it as a that is we can conclude as a FET is act as a voltage control resistor, which we also called it as a voltage variable resistor. Okay, so these are mostly used in the communication equipments. Okay, so these are the things I covered up to now. So here what we discussed up to now is I given some introduction to the transistors, what are the classification of the transistors. In that I explained about the field effect transistor classification, and then JFET, mainly concentrated on the JFET, and JFET means JFET construction details, after that working with the VI characteristics. So most important thing is the JFETs are the high capable of they are very less in size. So due to that size they are less power consumption. So as we require IC, whenever we want to fabricate an IC, so we require a very less power requirement, right? So if there is a less power consumption, then we are able to easily design a circuits with the very these junction FETs. Okay, with this I am going to conclude this my session, and next class I will explain the MOSFET. Thank you.